Sit close enough.
I'll introduce you. Good evening, everybody.
Good evening.
So Mick TZE, he's a troublesome character, as we all know. And he said to me about 6 years ago, he said, can you give a talk on Smith charts? I don't understand how to do Smith charts. And I said, right. And I thought about it, and I thought, you'd have to be a raving lunatic to attempt such a thing. So we parked the talk, and I said to Andrew Baird, would you want to give a talk on Smith charts? And he said, no, he said, you'd have to be a raving lunatic to give a talk on Smith charts. So the subject languished for a few years. And Steve said, I think I want to give a talk on Smith charts.
Tick one off your list.
And then we thought about it, we thought, well, that's all very well, but you're never going to explain the subject in an evening. So we thought, well, we'll do a series of talks, and Neil very bravely volunteered, just to try and stop us making too much idiots of ourselves, I think. So we've got a series of, it's actually 4 talks. They're not consecutive Wednesdays, there's a few things in between. But they all follow on from each other, so ideally you want to attend all 4 talks. Otherwise you're going to get really confused if you do the first and the last one or something. It won't make much sense. But Chris has very kindly offered to video it, and you're going to stick it up on the club website. So if you miss a talk in the series, and you decide the talk's really good and you want to see the rest, you can catch up by watching the videos. That was the idea. So without further ado, I shall introduce Steve, who's been a member of the club for about 2 years now, yeah. Big CW fan. And he's going to kick off this series of talks with a sort of introduction to impedance, really, and other things. At which point I shall sit down.
Well, thanks very much. I said part 1 because when I prepared this, I had the intentions of covering some maths and some geometry stuff, and then to get on to complex numbers as well. That just doesn't fit in one talk. So I'm not going to get as far as complex numbers, or in fact anything much to do with impedance. I'm just going to talk about waves and circles because I think they're interesting. If this is well received, you think it was interesting, you think you'd like to continue, I'm very happy to do another talk on complex impedance and the bits that I didn't fit in, which means that we'd have 5 instead of 4. I'm yours to command. If you're not interested in it, it's no skin off my nose, I'm not going to mind.
We've got to do it now, Steve, it's on the programme.
It's on the programme. Take it off. So I've called this Foundational Mathematics for Complex Impedance, Part 1. And as Andrew says, it's the beginning of a series of talks on complex impedance. And my intention is basically to set the scene by exploring some of the foundational maths that explores and underpins what we do when we are looking at AC circuits. So one interesting feature of our hobby is that there is a very wide range of exposure to and understanding of some of these ideas. There are people in this room who are or were professional engineers for whom this stuff is second nature. Some of us studied maths or physics at a fairly high level and have had some exposure to them. Many of us have forgotten everything we ever knew. Some of us simply memorise some facts and plumb the numbers into exam equations. And some of us might be in the early stages of understanding, maybe working towards a foundation or just past a foundation exam, and might not have learnt much about AC theory or reactive components. So I don't know where we sit in this room as a spectrum. I know there's a wide range. So I want to talk a little bit about my credentials. Well, I have 2 degrees from Oxford University. Unfortunately, they're in theology. And I am also a professional engineer. Unfortunately, a software engineer. So what that basically means is I have no credentials at all. What I'm going to present to you is how I, as an autodidact, have learned and developed some of my understanding around the ideas that you can't stop bumping into when you try to model and explore and manipulate AC signals. I am sure there are mistakes in this. I do not pretend to be an expert. Those of you who are experts, please be kind enough to tell me when I've got things wrong, preferably at the end of the talk rather than in the middle. So I'm going to start with an interesting demonstration. So I have made a pendulum here. I've made it from about 61 centimetres of whipping wire and a ferrite core looped around a skewer. And what I'm going to do is I'm going to set it swinging, and I'm going to let it swing for 20 swings, I'm going to time how long those swings take, and then I'm going to take an average time for the swing, and we'll look at it. Now, a pendulum's motion is very similar to the behaviour of a radio wave in that it oscillates backwards and forwards at a regular rate. So, I'm going to get my timer ready. Okay, the timer is ready. So, I'm going to swing it back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, I couldn't have done that better if I'd tried. So that was 31.47 seconds. And if you divide that by 10, for reasons I will come to in a moment, that is 3.147, which is pretty damn close to pi. So our pendulum is taking 1.5 seconds, roughly, to complete its swing. And so it's doing pi swings twice. What's interesting about that, when we double it, is that it becomes very close to pi. So, well, why is that? So I want to do two things here. Firstly, I want you to understand that pi is here in the middle of an equation about pendulums. In fact, it's 2 pi. And you will see 2 pi appear absolutely everywhere in electronics. It's all over the place. And the significance of that and why it is 2 pi will become apparent. And the second thing I want to show you is how, by selecting the particular length of the pendulum that I chose, I'm able to demonstrate to you that this equation is in fact accurate. So this equation says, and it's a simplification, but this equation basically says that the time it takes for a pendulum to complete its swing is 2 pi multiplied by the square root of the length of the pendulum divided by local gravity's acceleration. So if we want to prove that, what we can do is we can try to say, well, let's set it to pi. If this is true, let's make it be pi. So if this is true, pi is 2 pi times square root of L over G. And we want to work out how we can make that happen. Well, so if we divide both sides by 2 pi, then we get 1/2 is square root L over G. Now we'd like to get rid of that square root, so we can square both the sides. If we square both the sides, we'll get 1/4 is L over G. Now we would like to get L on its own, so if we multiply both sides by G, this will cancel out on the right, and you'll get L is G over the 4 if you swap the sides around. So now we know what we need to divide gravity by in order to get an L equal to pi. And the answer is 2.45 meters. Now, unfortunately, this room is not high enough to do a 2.45 meter pendulum, otherwise I'd have done it. However, what we can do is we can do exactly the same process by putting pi over 2 on the left. Pi over 2 divided by 2 is 1/4, and 1/4 squared is 1/16, and 9.81 over 16 is about 61 centimeters. So I made a 61 centimeter pendulum, and that's what we used. So we have shown that pi over 2 is 2 pi times 61 centimeters over gravity. So what I hope I've shown here is that periodicity and oscillation are inherently related to the constant pi, and thus to waves and to circles. So I now want to turn our attention to circles, and to do so I want you to imagine a Ferris wheel. There used to be one in Southsea before they took it down, so maybe we can think about that one. I want you to imagine that you have a friend who's on the Ferris wheel. Now, for reasons of mathematical fudging, I want you to imagine that they can arrive at 3 o'clock. They're not going to start on the bottom because that messes everything up. But they're going to arrive at 3 o'clock on the corner. So, if your friend is going round this Ferris wheel in an anti-clockwise direction, I want you to imagine that it takes 20 minutes for that wheel to go all the way round. So if you view that person from the side, You can see how far they're going round, you can judge the speed of their journey, and in fact they're going to cover about 5% of a circle every minute. So now what I want you to do is I want you to imagine that you're standing at the end of the wheel, so you're looking just at its edge, so you can see the cars going up and down. So from this angle you can't see how quickly your friend is going round the wheel, but you can see how high they are. Now if your friend were looking at their phone, which knows the height above sea level, and they texted you every minute, and you plotted their height against time on a graph, the shape that that graph would show would be instantly recognizable as what we would call a sine wave. So I've written a little computer model to show this. So I'm going to try and run the computer model. This is where the demo gods have to smile on me.
It's not children or animals, you should be alright.
Oh, demos are just as bad.
All right. Okay, so this is our person going round the Ferris wheel. And they're going round relatively slowly. So this is where we see them. And it starts again. So when we look at it from the side, we're not seeing much that's very interesting. So now let's look at it from the end. So this is what you see from the end. Your friend is going down, and then back up again. And up. And back down again. And now the third one. Oh, cool, blimey, doesn't it look like a sine wave? Well, I never. So an important thing to notice is that we could have put time, or indeed we have put time on this axis. And that's related to every minute that your friend texted you and you recorded the height. But we could just as easily have tracked how far round the wheel our friend was. Those two are so closely related, I would actually go so far as to say they are identical. All right, we'll come back to the models in a minute. So, the conclusion I want you to take away from that is that we get a sine wave from circular motion, and the inverse is also true. When we see circular motion, we get a sine wave. When we see a sine wave, there must be circular motion. So let's remind ourselves about some facts about circles. So one thing that we know is that for any circle of any size, the ratio of its diameter, so a line drawn through the middle, through the origin, to its circumference is a constant number. That constant number is, of course, pi, 3.14159265, etc., 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 etc. So, I have here a mountain bike tyre that I nicked from my son. Now I've measured its radius, so half the diameter, and I've cut out some rope of the same length. Now conveniently enough, This radius is in fact about 1 foot, but it doesn't matter. We're going to call this radius length 1 something. We call it 1 SNS. Doesn't matter what you call it. So, when you make a circle and you set its radius to 1 something, we call it a unit circle. Because whatever you decide to measure it in, its radius is going to be one of those. So, I need a volunteer now. Who's a convenient volunteer? I reckon Chris is always good for volunteering. Come on, Chris, come and help me. I need you to hold the tyre and possibly help maybe with some tape.
Okie doke.
So, what I'm going to do is I'm going to take these bits of rope and I'm going to wrap them around. I'm going to wrap them around, starting from our favourite place, about here. Put your finger on there. So that is 1 radius worth of rope. Okay, now I'm going to do a second radius worth of rope. Start about here. Here. And then I'm going to do another radius worth of rope. It's not very sticky stuff, this, is it? I think you get the point.
I'll keep tearing my
There you go. That's enough. Okay.
Are you
So-
only going halfway, are you?
Oh, we're only going halfway. Now, unfortunately, because we've got a bit of a sag, it's almost exactly half. But you can see it's not half. So you can see that 3 radius lengths bit of rope stretched around the outside goes 3 lengths round, but not all the way. Now, this is really important because the bit that's left over is about 1/7 of a length of rope. 1/7 is, curiously enough, 0.142. So we need 3.142 radius lengths of bits of rope to go halfway around the tyre. In other words, we need pi bits of rope to go halfway around a circle. And 2 pi to go all the way around the circle. Now this shouldn't come as a surprise, since we know that pi is the ratio of the circumference to diameter, and we know that the radius is half the diameter. However, it is noteworthy that our friend 2 pi has appeared again. Thank you very much, beautiful assistant. So, if I now were to take those bits of rope and make a cheese-shaped wedge, I'm going to try and do that on the screen. If I were going to try and make a cheese-shaped wedge with 1 bit there, and 1 bit there, and 1 bit there, you'll see they're all the same length because it's a unit circle. What happens then is we create a very important shape because the angle here between the bits that make up the wedge is a mathematically significant number. In fact, it is so significant it has its own unit. It's called the radian. So 1 radian is the angle made when a radius length bit of string is wrapped around the outside of a circle and its ends are connected to the origin. So another way to think about this angle, 1 radian, is that's the amount of time we go round the circle. That's how much angle we've gone round the circle if we've gone round 1 radius worth. This proves to be extremely convenient because halfway around the circle is pi radians and all the way around the circle is 2 pi radians and 1/4 of the way around the circle is pi over 2 radians. In engineering, we tend to prefer to measure angles in radians and not degrees. Degrees are actually an arbitrary relic of Babylonian astronomy and their obsession with the base 60 counting system. So how about we don't? So, when we earlier talked about the speed at which our friend was going round the wheel, we mentioned that 5% of the wheel was covered in 1 minute. So this speed actually has a specific name. It's called angular frequency. And it's measured in radians per second. Now we know that our friend is covering 5% of the circle in 1 minute. Now 5% of 2 pi is the same as pi divided by 10, or 0.314 radians a minute. Now if we divide that by 60, we get about 0.005 radians a second, or pi over 600. This is a very important fact to know when looking into circular motion. How fast are we going round the circle? And this has its own Greek letter, omega, the same omega as in ohm, but just little. So omega, radians per second, is measured with the letter omega. Now, when we talk about the frequency of a signal, whether that be 7 megahertz or 50 hertz, that's directly related to angular frequency. In fact, angular frequency and regular frequency are related by, you guessed it, our old friend 2 pi. Angular frequency, W, is 2 pi times f. And the frequency is the angular frequency divided by 2 pi. Okay, let's go back to our graph now. This is the graph that we recognized as a sine wave. So let's be a little bit more specific at what we're looking at. When we say that we recognize the sine wave, what we're actually saying is we recognize that this looks like the graph of the sine function. So a function is an operation which, when given an input, returns an output. You can think of it like a black box. If I had a black box that doubled money, and I put 50p in, I get £1 out. If I gave it £5, I get £10 out. A function is just a black box that does the same thing all the time. So the sine function takes in an angle in radians, and it returns the height of the wave between 0 and 1 on either side. So that's actually between -1 and 1. Now we can understand this more deeply by looking at our friendly unit circle again. So let's imagine if we plot our unit circle on a graph with x and y coordinates. So when your friend starts their journey over here, they're starting at 0 on the y-axis and 1, because this is 1 radius, and 1 on the x-axis. And at this point, the angle against the x-axis is 0 radians, and sine of 0 is 0. As your friend moves around the circle and the angle increases, the position along the y-axis changes. So we're up here now. This y value is what the sine function returns. That's what it gives us. So in this case, pi over 4 radians, which you might recognize as 45 degrees, at this point your friend is on the way up the wheel. So the sine of pi over 4 is 0.707, which you might recognize as also square root of 2. At the top of the wheel, the angle is pi over 2, or if you prefer, 90 degrees. And the sine of pi over 2 is 1. As we go further around, the symmetry starts to show. Although the angle is bigger, like this is now an obtuse angle.
Sorry, isn't that 1 over the square root of 2?
Isn't what 1 over the square root of 2?
Isn't the square root of 2 1.42? 0.707 is its reciprocal.
Yes.
Sorry, I've also got a degree in maths.
No, it's good. Yep. So as we go further around, the symmetry starts to show. So the angle is bigger, but 3 pi over 4, and the place on the axis is the mirror image of the other side, so it's back to 0.707. Halfway round, we're back to where we started. The angle is pi radians, but the sine of pi is 0. As we carry on round, we start to get negative numbers on the y-axis in the same symmetrical way, and as we get to the bottom, we get to a trough of -1. So we often take it for granted that you can get the sign of a number from a calculator or from a computer, but it's not magic. It's just geometry. There's nothing special here. The values are calculated based on relationships in the unit circle. So some computers, well actually probably no computers now, but some computers and calculators use lookup tables, and humans used to use lookup tables. But you can also calculate them using an algorithm, and if you're curious, you might want to explore the Taylor series for calculating sine, but we won't look into that today. It's very interesting. Okay, so we spent a lot of time with Ferris wheels and bicycle tires. The point I'm trying to make is that the behavior of waves in AC circuits is exactly the same as the behavior of our friend going round a Ferris wheel. And understanding the maths of a Ferris wheel and the unit circle is a valuable foundation for what we're going to do in the next few weeks. So I want to move our conversation away from circles for a moment and talk about DC circuits. So let's start with a trivial example. If we have a circuit that's made up of a 12 volt DC power source and a 10 ohm resistor, we know that 1 amp of current will flow because current is the ratio of voltage to resistance. And importantly, this is linear. It doesn't slowly build up to 1 amp or vary between half an amp and 1.5 amp. It's just 1 amp. You switch it on, it's 1 amp. You switch it off, it's not. It's a straightforward thing. Well, if we put a capacitor in the circuit, things change. So this switch here in the middle is just to make sure that the capacitor is discharged when we begin. So when we connect the battery, what's going to happen? Well, at first there's no charge in the capacitor at all. So the current can flow freely. In practical terms, the capacitor is, for a very brief period of time, short circuit. So Ohm's law tells us that 1 volt over 1 ohm will give us 1 amp of current. So right at the beginning of time, there'll be a rush of current and we'll have 1 amp of current. But then, as the capacitor starts to charge up, the difference in voltage across this resistor will start to tend towards 1. So the difference between the voltage source and the amount stored in the capacitor will get closer and closer and closer, and eventually the capacitor will effectively be open circuit. No current will flow. If you want to think about it in other ways, the resistance of the capacitor is effectively infinite, and the current is effectively zero. But this does not happen linearly. So going back to our old friend, the bicycle tyre. If I'm pumping up a bicycle tyre, at first it's really easy to pump up. And I can get it to be pretty firm very, very quickly. But to get from pretty firm to really hard, it gets tougher and tougher and tougher, because the pressure in the tyre is pushing back until either I just can't push any more air in because I'm not strong enough, or I push so hard that the tyre bursts. And capacitors are exactly the same. So the charge of a capacitor is an exponential function. So after 1 second, the capacitor is about 63% full. And after 5 seconds, it's near as damn it completely full. And the reverse is also so. After 1 second, only a small fraction of the original current is flowing, and after 5 seconds, as near as damn it, none is flowing. So we can see from this graph that 2 things are changing in this circuit: the amount of current and the amount of voltage. When we see this sort of behavior, we're often interested in 2 things. We're interested in the rate of change. How quickly is the voltage increasing or the current decreasing? And we're interested in what's making that happen, what's the driver, what's kind of responsible, what's governing that change. And in our case, it's the voltage that makes all the difference. When there wasn't much voltage across the capacitor, there was a lot of current flowing. But as the voltage increased, the current decreased. And in fact, the faster the voltage increases, the faster the current decreases. This relationship is crucial in physics, and it's described by something called the derivative. So the derivative describes and governs the rate of change in systems. In our case, the rate of change of current in the system is directly related to the change of the voltage. So the equation that describes this formally is this one. Now, we don't need to talk about differentiation and calculus to understand the point. The equation is pretty clearly saying that the current at a point in time is related to the difference between the voltage at a point in time multiplied its capacitor. So in a DC circuit, this is relatively straightforward. There's just an exponential relationship between the capacitor and the resistance, and it goes up and then it stops. But what about if we're in an AC circuit? What happens then? Well, let's go back to the Ferris wheel. If we look at the animation of the Ferris wheel going from the end, we'll notice something significant. The speed of the ascent and the descent is not linear. Our friend started zooming up and then slowed down, and then zoomed down again before slowing near the bottom. So what's going on here? This should be familiar territory. We're interested in the rate of change and what governs the rate of change. So, to understand this a little bit more, let's scramble underneath the Ferris wheel. This time we're going to have our friends start at 3 o'clock as usual, and this time we're doing the recording. We're going to go underneath And we're going to put a stick in the ground at the point where our friend is, and then we're going to set a timer for 1 minute. And every minute our timer goes off, we're going to crawl along a little bit until we're underneath our friend, and we're going to put another stick in the ground. And we're going to keep doing that 20 times, at the end of which we'll have 20 sticks in the ground. And we can then plot our distance out from the centre of the wheel against time. Now, you might not immediately recognise the graph that comes up in the same way that you recognise the sine one, but you ought to notice it has a certain similarity to the sine graph. Now, I've written a little computer model to do this very same thing. So let's see if we can make it work. So again, we're measuring time, and on this axis we've got what I'm calling horizontal displacement. How far out from the middle of the Ferris wheel are we? So, this shape here, it looks a bit like a sine wave, but kind of in the wrong place. You sort of squint at it, you're like, well, it's kind of a sine wave, and of course it's a cosine wave. And the function we've drawn is the cosine function. So when we run the simulation, we can see that at the start, the horizontal displacement was at the maximum. Our friend was all the way out there. So this corresponds to the cosine function being equal to 1. So at the beginning of time, our cosine function is up here, and our sine function is down here. Now, we already know that the speed at which our friend moves vertically, it begins quickly, and then it slows down, and it speeds up again. And actually this makes sense because we can see this slope is steep, and then it softens out, and then it's steep, and it softens out. So the slope of the curve decreases as the amplitude of the cosine function goes down. So when our friend is right at the top of the Ferris wheel, when our sine function is at its highest, they're moving so slowly, they're almost not moving vertically at all. And at this point, most of the momentum is in fact horizontal. And on the other hand, when our friend is halfway between the top and the bottom, they're moving really fast vertically, but horizontally almost not at all. So in other words, when the cosine function is at its highest, the speed in the vertical direction described by the sine function is at its maximum. So that's why the rate of change of the vertical motion, which the sine function describes, is governed by the cosine function. Mathematically, we can say that cosine is the derivative of sine. Now, we already noticed that the cosine function reaches its peak before the sine function. You can see that clearly in the diagram. So we say that the cosine function leads the sine function. And if you look at the difference between the peaks, like this one and this one, or the lines, this one and this one, or here and here, you can see that the gap is always about 1.5 radians, or more specifically, pi over 2 radians. Pi over 2 is equivalent to a quarter of a circle, or 90 degrees. And this difference in peaks is something that we'll come to a lot in the future. It's phase difference. When I first learned about this, I found it really confusing, because on graphs it was often labelled as time and measured in degrees. That didn't make any sense to me at all. However, if we think about the relative positions of things around a circle and measure it in radians, the concept becomes clearer. So instead of thinking of terms in time alone, if we visualise these functions on the unit circle, it makes phase difference much easier to understand. So before we move on, I want to be explicit about what we're looking at when we look at a sine wave that represents voltage, rather than the height of our friend. So this formula basically says, and we're familiar with all of these terms now, this formula says that the voltage at any point in time is the maximum voltage, the peak voltage up here, the peak voltage multiplied by the sine function, taking as its argument the angular frequency at a point in time. Now, we sometimes add phase shift to this, but we can come to that another time. Now, we know what all of these things mean, and they're really important when we want to make the transition to thinking about AC. So now that we've got a head around what voltage looks like over time, let's go back to the equation that describes the behaviour of current in a capacitor over time. So we asked ourselves the question, what happens if this bit here is oscillating rather than a direct current? Well, now we know that the oscillation of voltage is described by this one here. So the behaviour of this is V0 sine omega t. So what that means is that we can stick that there. So having substituted the sine function, it looks like this. Again, it's not actually that hairy. Don't need to get too overwhelmed. But because we want to know the rate of change of the sine function, we need to take the derivative. Now we know that the derivative of sine is cosine, and we multiply by angular frequency because that describes how quickly the wave is oscillating and will make a difference to the rate of change. So we can bump in this bit here, and the final result that we get is this. The current at any time is the capacitance multiplied by the angular frequency multiplied by cosine omega time. So finally we reach this, which shows us how current behaves in the presence of alternating current. And this is what it looks like. Now that should look extremely familiar. In an AC circuit involving a capacitor, the current leads the voltage. Now you might have memorized this. You might have said horrible things like Eli the Iceman or Civil or something like that. I don't like acronyms like that. I'd rather actually understand how these things really work. So I hope after tonight's talk, you already knew this, but you understand where this comes from. So I'm going to pause there because we could go on like this for a lot longer. But my contention is that understanding circles, understanding 2 pi, understanding radians, and understanding circular motion are at the heart of everything that we do in AC. And understanding that has helped me in my journey of trying to understand things. So next time, having understood the idea of phase shifts, and having looked at how capacitors behave, we might want to look at inductors. And we might want to understand that inherent to capacitors or inductors are phase shifts. What we need to do is we need to understand how to measure and model and understand them. And that requires us to talk next time about complex numbers and phasors. So, if you will have me, I would be very, very pleased to talk about complex numbers and phasors in the next thrilling installment.
Doesn't really lead to